Hi, Syed.
Hello,
How are you doing?
I'm doing fine. How are you?
Pretty good. Sound check. Sound okay?
Yeah, everything sounds good.
Okay. Okay, let's let them through.
Okay.
Morning, everyone. It's a rainy day here in Toronto. Rainy. Okay. It's again. This is only for emergency purposes. I'll put the YouTube link. Oh, okay. And then let's see. Oh, what is going on? Let's try that again. Okay. All right. Very good. Except for one thing. What is going on here? Oh, I see. It wants to keep me in this position. That's okay. I can deal with that. Okay, let's take questions. Let's take some questions before we start. Any questions? Your new assignment is out. The old assignment is handed back. You should have all gotten links to those. There's just a couple words about what's going on in the piazza. So people are using the piazza, and for the most part, it's going pretty well. There's a number of questions which are of the form, why, I didn't get the question on my assignment right. Why? Okay, so this is, no one really cares whether you got your question right or wrong. Okay, just ask the question, like try to condense your questions into mathematical content, right? So it's like focus on the part of the question which you don't understand and ask about that. Okay, and if you're not getting an answer, if you're not getting an answer to your question on Piazza, it's probably because your question is so bare bones that it doesn't give anyone, like no no one even knows what to do with a question like that because it's just completely vague. So if you don't get a question if you don't get an answer on Piazza, you should not try to email people then. You should just try to improve your question or give some more detail. Hopefully Walid will prompt you for this, but if he doesn't, just try to get your answer.
So there is such thing as a stupid question?
Well, I'm saying they're almost not even questions because they're more like complaints. I didn't get my question. I didn't get my assignment. I didn't have perfect mark on my question. I don't know why. Well, okay, that's not a question that everyone is interested in. It's not like you shouldn't like be putting your personal problems on Piazza. But in general, it's going pretty well. I think a lot of the answers, even from the students, are not bad. Okay, so no one has any questions because you're too you're still half asleep. You're not even fully conscious yet. That's fine. Let's move into the material, and hopefully you'll if you have trouble during the lecture. By the way, like these Zoom lectures, I mean, I can't even imagine how terrible it must be to like just be sitting down and listening to one Zoom after another. And I have to do even more because I'm meeting all my students and I'm going to conferences and everything is on Zoom. So my advice is to if you start dozing off or something, try to do some sit-ups or push-ups or something, and get your blood flowing. And maybe put some boxes on your desk so that you can stand up while listening to these Zooms. If I wasn't standing up during this class, I think I would just keel over with the Zoom fatigue. Okay, so we talked about Gaussian elimination algorithm, right? So we talked about we start with a list of vectors in V. And a basis. Here, K is different from N. N is the dimension of the space, of the vector space, but K could be anything. It could be less than N, could be equal to N, could be greater than N. Okay, it's some list of vectors. It doesn't matter how long it is or how short it is. The basis, is the basis. So it's like a coordinate basis, or like unit vector basis, similar idea. Okay, and so the first step, so the first thing that you need to do is convert this into some kind of numerical data. And what you do is you take V1 and write it as A11 E1 plus A12 E2 all the way to A1n En. And you do the same thing for all of the vectors, expressing each vector as a linear combination of the basis vectors. Okay, and so as a result of this, you extract a K by N matrix. So we get a K by N matrix. So we get a K by N matrix, which represents the data. Okay. And then what we're going to do is apply a succession of elementary row operations. So we do elementary row operation 1, we do elementary row operation 2, we do a bunch of these. Okay. And every time we apply one, we change the matrix. We might switch two rows, we might multiply a row by a constant, or we might add a multiple of a row to another row. Right? Those are the possible elementary row operations. You have switch, you have scale, and you have shear. Okay, these are the allowed elementary row operations. Okay, and you pick a bunch of these, and then at the end you end up with a simpler looking matrix which has an echelon form. Actually, sorry, let me redraw it. So the echelon form could be something like this: 1, 1, 1, 1. And then here you could have anything at all and 0. Okay. So, okay, and what we're guaranteed, so the output is a matrix in, it's also a k by n matrix. The size, the shape of the matrix has not changed. And this is in row echelon or reduced row echelon form, depending on how far you want to go with the algorithm. Okay, and you're guaranteed that the new matrix, the final matrix, the output, represents a list with the same span as it had originally. Okay. Now, notice. Okay, I just want to make a few comments. So just notice that it might be that you have some 0 rows at the bottom of the matrix, right? The echelons, the staircase, could go and end at a position which is not the bottom of the matrix. So that means that you have no non-zero elements on the last rows. This could happen. Okay, and what this means is that the new list will look like W1, W2, up to WK. That will be the new list, but the last few entries might be 0. Okay, and so what is the significance of this? Well, the significance of 0 rows in the result is that there are redundancies in the in the original list. Okay, you can see this in several different ways. So one way that you can see it is that the span of this new list is the same as the span of the old list, but this new list has these zeros. So that means that actually the list is kind of shorter in a way. If you ignore the zeros don't contribute anything to the span. So you could just ignore them, and you could just say that I could have shortened my list. I could have shortened my list right here, let's say, right? And I would get the same span. So what that means is that I have a shorter list which spans the same space. And that is telling us that there was the original list was linearly dependent. Okay, that's number one. And then a related remark is that the non-zero rows in the result are automatically linearly independent. Okay, so these ones here, these rows are linearly independent. There are no redundancies. Okay, and the reason for this is pretty easy to see, and it has to do with the fact that every one of these rows has an echelon number 1 in a specific position. Okay, and that this thing, that there are none of these echelons are in the same column. They're all in different columns. Of course, it can't be that this couldn't have been in the same column as this one, because this one, remember that he's a psychopath. He killed everyone beneath it. Okay, so why are they automatically linearly independent? Well, let's say that we have just a staircase. Well, let me not make it so symmetrical. Okay, and let's say that we have a 1 here and a 1 here. Okay, and okay, and let's say that so remember that that the position. Well, sorry, this is a little bit too messy. Let me just give an example to give you the idea. I think it will be entirely super clear. So 1, 2, 3, 4, 1, 4, or 1, 6, let's say, and then 0, 0, 0. Okay, this is a 3x4 matrix, which is in reduced, which is in row echelon form. This is in row echelon form. Okay, I have my echelons right here and right here. Okay, and remember that the meaning of this matrix, so this matrix, now we're interpreting it as data, which defines a list of vectors. So the corresponding list is W1. How many rows are there? 1, 2, 3. W1, W2, and W3. And W1 is equal to 1 times E1 plus 2 times E2. I'm using the same basis to describe this thing. Right? And W2 is equal to 1 times E3 plus 6 times E4. And W3 is equal to 0. So these are my 3 vectors in the new list. This is the new list which I would have obtained as the result of the algorithm. Okay. And all you need to do is to show that. So if we want to show that W1 and W3, W1 and W2 are linearly independent. Okay. Just imagine what happens if you have, let's say, AB, constants AB, which give a trivial linear combination. So let's say we have AW, so if AW1 plus BW2 is equal to 0, okay, we want to show that A equals 0 and B equals 0. So we want to show that the only way we could have a linear combination of W1 and W2 is if the combination itself was 0 with 0 coefficients. Okay, so how do we do that? Well, let's just focus on the position where there are ones, right? So if I say that, if I look at this equation, I'm taking A times W1, and so plus B times W2, right? And if I look at the coefficient of E1 of this sum, what is the coefficient? Well, you see that W2 doesn't have any multiples of E1 here. So when I multiply B times W2, that is not going to contribute to the coefficient of E1. Okay, the coefficient of E1 is going to be exactly A, because the coefficient of E1 in W1 is exactly 1, because it's an echelon. So the coefficient of E1 is A. Okay, and that's, therefore, because I need, because this combination has been expressed as a sum of coefficients multiplied by a basis, the only way that this can be 0 is if all coefficients in front of the basis are 0. Okay, and this must be 0. And the coefficient of, now which other coefficient do we care about? We're going to look at this one, the coefficient of E3, because there we know that W2 has 1. So the coefficient of E3 is what? Well, there will be a contribution from W1, which is exactly 3 times E3. That's the coefficient of E3. But that is going to be multiplied by A. So I'm going to get 3A plus B. And this must be equal to 0. Okay, so this implies that A is equal to 0, and plugging A into this equation, we get B equals to 0. Okay, so anytime that we have something like that, where W, when I express it in terms of a basis, if I have like 1 times EI plus something times EJ plus other junk, which are other multiples of other basis elements, okay? And if I have, let's say, W prime, which is equal to 1 times EJ plus higher terms, 0 times EI, okay? So whenever I have a situation like this, where there are two basis elements, EI and EJ, where one of the vectors has a coefficient 1 here, the other one has 0, but this one has 1 somewhere else, okay? Anytime this occurs, and this is how echelon form is always looking, right? Echelon form always has, this is a kind of abstracted echelon here, okay? Whenever this occurs, when I take A W plus B W prime, okay, this has EI coefficient A and EJ coefficient AC plus B. Okay, and if we set this equal to 0, this implies that all the coefficients in the basis are equal to 0, which means that A is equal to 0 and AC plus B is equal to 0. But this implies that this term is gone, and so we just get A equals 0 and B equals 0. Okay, so any two rows that are non-zero rows inside the echelon form are always going to be linearly independent, and the same argument will hold for any combination of those rows. So you could take all of the rows together, multiply, take a linear combination, and then just go through them from top to bottom, and you will get that each one successively must, each of the coefficients must successively vanish. Okay, so this is the argument for why this this holds. Okay, so right away now you can see what's happening. So we can conclude. Let's conclude that the non-zero rows of the row echelon or the reduced row echelon, because reduced row echelon is a particular type of row echelon form. The non-zero rows of these forms represent a basis for the span of the original list. So you remember all these questions that I was asking in the assignment about, here's a subspace. Let's say that I gave you the spanning set for the subspace. I gave you a list of vectors that spans the subspace. Then you might want a basis. You want a much more efficient set of workers. Find me a basis for the subspace. All you have to do is do row reduction until you get row echelon form. Look at how many non-zero rows you have, and that's it. That's your basis. Okay, any questions about this?
So Neil, you have a question?
Yeah, go ahead.
In general, when we're doing Gaussian elimination, I know like for when you're doing this like numerically, sometimes you try to pick a specific order for like what row you're going to use as like the pivot. Because like you don't want to divide. So you like numerically, if you're doing this, you don't want to divide by very small numbers. So you try to make sure that you were only like when you were dividing out all of the.
Sorry, you may have an interest in numerical analysis, and
So I guess
dividing
my
by
question
small
was,
numbers
I
and
think
floating
you
point
can do
arithmetic.
this and
But
get
I'm not going to answer questions about that.
Yeah, I guess what I mean is depending on how you swap the rows and how you divide, and you can get like different bases that span that same.
Correct. You'll get different bases. Yeah.
So will all of those be marked correct for like homework, or do they expect like a
I don't
single?
know. I hope so.
Good.
Why do you think that they wouldn't be correct if they are bases? If it's
Well,
still a
at least
basis,
I think
why do you think?
well, I mean, you know, if in sometimes you're expected to implement in a specific way. I didn't know if that was the case here.
No. You're looking what you're doing right now. I mean, I'm just answering this way for the benefit of everyone. It's a perfectly valid question. But what you're doing now is looking for trouble. That's what you're doing, literally. Right? Because it's like, you know perfectly well that one basis and another basis, they're still going to answer the question. So you know that it should be marked correct. Okay,
Sure.
more questions.
So Daniel, you have a question?
Yeah, hi. Why do we take the rows of the matrix as the basis and not the columns?
Well, there's a convention when we're writing things down on a page. And if you want to develop your own conventions, that's perfectly fine. But then don't talk to me about it. There's a convention for how things are written, right? And the important thing is not really, when you're talking about a convention, right? We could have done it in the opposite way. So there's an ambiguity. We could have decided to do it in a different way, but then we would have to do column operations. So it of course it doesn't matter, because you can just take your piece of paper and rotate it 90 degrees. Okay, the important thing is to know the convention and to understand how to implement the algorithm. I mean, the computer doesn't know which one is which.
I see, thank you.
Sorry, I mean, I don't mean to give such sarcastic answers, but maybe it's better if I give sarcastic answers so that you kind of remember the answer. I don't know. Next question. Okay, so let's get on to the next thing. So I just explained one skill, right? The skill of finding a more efficient basis, a more efficient spanning set. In fact, finding a basis for a certain subspace. That's already, we did that. So that's the correct way of doing it. Okay, let's do a famous example. Okay, suppose that I have a vector which is a vector in a two-dimensional space. And I have another vector in a two-dimensional space. So you could even draw them here. Okay. And you write them like this. So I don't know what the coefficients are. I'm going to do it in general. So this is two general vectors in two dimensions. I have a length 2 basis. I've expanded them out. So I get a matrix, which is A, B, C, D, the 2x2 matrix. Okay. And the question is, under what condition is V1, V2 linearly dependent? Under what condition? So we know geometrically what that condition is. It's just like, in order for V1 and V2 to be linearly dependent, they need to line up. Okay, but the question is, how do we express this fact in terms of the entries of the matrix, in terms of these numbers? How do we express the fact that the two vectors are pointing in the same direction? And by this, I mean, like one of the vectors could be 0 and they would still count as being linearly dependent. Of course, everything is linearly dependent with 0. If 0 is on the list, it's obviously independent. It's obviously dependent, sorry. Okay, so under what condition would this be possible? So let's analyze the matrix. So I'll start with A, B, C, D. And so the first step is that I need to find the earliest non-zero number. So let's assume, I mean, there's two possibilities. Either A is non-zero, in which case we can use A as the earliest non-zero entry, or A is 0, and then if A is 0, then C must be non-zero. Well, let's break it down into three cases. Either A is non-zero or A is 0. And if A is 0, then either C is non-zero or C is 0. Okay, so those are the three cases. So let me write that. So if, let me just move this over. Okay, so if A is non-zero, we can use it we can place it at the top. It's already at the top, so I don't need to switch. So then I scale. Scale by A inverse. So I'm going to multiply the first row by A inverse. And that I'm using the fact that A is a non-zero element of a field. Okay, so this is the next step. God, time flies. Okay, and then 3 shear C away. So I'm going to replace R2 with R2 minus C times R1. Okay, and now I've got it into row, well, okay, technically, in order to get into row echelon form, I would need to I would need to scale the second row so that there's a 1 there. But the problem is that entry there might not be non-zero, right? So now we need to analyze this at this point. So we observe this, so we inspect this. Okay, and what do we see? Well, we see that this is potentially, so there's two cases. So A, D minus A inverse BC could be non-zero, okay, in which case we can scale the second row and get 1 something 0 1. Okay, and because I have row echelon form and because there are no 0 rows, we know that these two rows are linearly independent. So we get, this is linearly independent. Okay, so the other possibility is that this quantity here, D minus A inverse BC, is equal to 0. And if this is equal to 0, then we've got a 0 row, and we're already in row echelon form. Okay, and this means that the list is linearly dependent. Okay, so here's our condition. So if A is not 0, the condition for linear dependence is this equation. Okay, but it looks a little ugly because it has the A inverse, but A is non-zero, so I could just multiply through by A, and I just get this, AD minus BC is equal to 0. Okay, now, so that is a full analysis of the linear dependence in the situation where A is non-zero. So if A is equal to 0, right, then we would want to use C. Okay, now, so if C is equal to 0, then we have a problem, which is that both vectors are basically pointing in, they're just multiples of E2. So if C is equal to 0, then we get linear dependence right away. Okay. So the next case is that, so linearly dependent if A is equal to 0 and C is equal to 0. But note that this condition is a special case of the previous condition. If A is 0 and C is 0, then this quantity AD minus BC will automatically be 0. So this is taken care of by this condition. So we've taken care of that. We know we would detect this possibility by just testing AD minus BC. If we find that it's 0, then we would not be led astray. It would still be linearly dependent. Okay, so so if C is equal to 0, it's linearly dependent automatically. But what about if we're still underneath this case, and if C is not equal to 0, then we use C as the early bird. Okay, and we would move C to the top. So we would switch, we would scale. We would shear. And we would get this. And then we do the same analysis as before. It's exactly the same as before, same analysis. And we would see that we get linear dependence if B minus C inverse AD is equal to 0. And this happens if and only if CB or BC minus AD is equal to 0. Okay, so in this, so now we've gone through the whole tree and we see, well, guess what? We get the same equation as we got before, right? If AD minus BC is equal to 0, then BC minus AD is equal to 0. So all roads lead to this same equation, okay? And therefore, V1, V2 is linear dependent if and only if this single polynomial in the entries, AD minus BC, is equal to 0. Okay, so what that means is that this polynomial in the entries of the matrix, the polynomial AD minus BC, okay, determines whether the list of vectors is linearly dependent. AD minus BC determines if the list is linearly dependent or not. And that's why it's called the determinant. Of A, B, C, D. Okay, so it's a simple function, a polynomial function in the numbers that occur in the matrix. And if that function is equal to 0, you're guaranteed that the rows of the matrix are linearly dependent. And if it's non-zero, then you're guaranteed that the rows are linearly independent. Okay, so note, this is something very important, that if AD minus BC is not equal to 0, okay, here's an important remark, that if AD minus BC is not equal to 0, i.e. we have linear independence, okay, then if we wiggle the values A, B, C, and D a tiny little bit, right? If we modify, if we perturb the matrix just a little bit, we perturb the matrix a small amount, AD minus BC will remain non-zero. Okay, so I just mean that, you know, if AD minus BC is non-zero, it's equal to something. It's equal to some number, right? And as long as you modify AD BC for sufficiently small deltas, right, then you will stay within epsilon of AD minus BC, because this is a continuous function. This is a continuous function of A, B, C, D. Okay, and so what that means is that if you find, if you find some vectors which are linearly independent, and if you move the vectors just a small amount, a sufficiently small amount in any direction, right, they will stay linearly independent. But the same is not true in reverse. If you have vectors that are linearly dependent, like for example, if they lie in a plane, and if you modify one of the vectors ever so slightly up, then they can become linearly independent. On the other hand, okay, if we have linearly dependent vectors, a small modification may make them independent. Okay, so we say that linear independence is an open condition. Okay, this is a, oops, great. This is a kind of important idea. Okay, so this was just an example. It was an example of applying Gaussian elimination, the Gaussian elimination algorithm, to a 2x2 matrix, or to vectors which are in two-dimensional space. Any questions about this?
Gurmanjot, you have a question?
Yeah, I was just wondering, like I'm sure, I'm sure you're aware of like the general, like concept of determinant for like much bigger matrices, or like bigger square matrices. So I was, wondering if was that concept of determinant for like larger matrices constructed out of like the same, like Gaussian elimination process for like a general set of like entries, or would there be a different way of constructing like that definition of a determinant?
Well, the definition of determinant has many possible ways of defining it. There's with something fundamental like that, there's always many equivalently good ways of getting at it. However, with Gaussian elimination, you could get it. And in fact,
Okay.
The interesting thing is that from a computational point of view, right, doing Gaussian elimination is extremely rapid and efficient. Computing determinants is not, because computing a determinant involves many more multiplications and additions than Gaussian elimination does. So it's kind of, that's something to keep in mind. So in fact, when you are actually checking numerically whether a gigantic matrix of thousands of entries is linearly independent, you would actually do it way faster by doing Gaussian elimination instead of computing its determinant.
Okay, got it. Thank you.
But anyway, we'll get to determinants later on if possible. I would like to discuss determinants in general, but determinants are kind of they obscure a little bit because the determinant is a kind of complicated object. It's a very high degree polynomial object, and it obscures somehow what's going on in linear algebra. So that's why the textbook de-emphasizes determinants. I mean, he has a very good point about how linear algebra used to be taught very much focusing on determinants all the time. And this is in many ways not a good idea. But of course, you do need to learn it at some point. It's an amazing thing. So, okay, next.
All right, Hongjia, you have a question?
Yeah, just a small question about, so regardless if you have a 2x2 matrix, a 3x3 or 4x4,
Yeah.
you go through the same process, right?
Yeah. Yeah.
Okay. Yep. Thank you.
Okay, thanks.
And Sungho, you have a question?
Yeah, so up to what extent is the modification small enough for your
Yeah, well, you need to know about continuous functions. So it's about delta and epsilon, right? If you continuous function means about the delta epsilon thing. So if AD minus BC, that's just a polynomial function, right? If it's equal to a non-zero number, right? If it's equal to, you know, if here's your real, oops. If here's the real line, here's 0, and here's your determinant AD minus BC, right? So the point is just that, you know, if you want to remain within this region, if you want to remain away from 0, right, the fact that the function is continuous is telling you that there exists a delta, so that if you stay within delta of A, B, C, and D, then AD minus BC will remain within epsilon of the value that it had. So the definition of continuity guarantees existence of delta, such that in that neighborhood, in the delta neighborhood of the initial point, you stay safe. In order to figure out what that delta is, then you need to do a little more analysis. You need to do an estimate about the size of the derivative of the determinant and so on. And there are formulas for such things.
Thanks.
Okay, let's, we only have 10 more minutes. Let's see what I can, okay, so, okay, next skill that you need to know is how to solve linear equations. Okay, so, solving linear equations. Okay, so if you have, let's say that f, yeah, so suppose that, so usually when you are writing linear equations, you're writing it in Rn. So I'm just gonna focus on that case, just to teach you the technique, but the same holds for any field. Okay, so let's say that we have find, so the solving linear equations are find, the question is find all x1, xn in Rn, satisfying f1, let me just call this x, f1 of x equals 0, f2 of x equals 0, up to fk of x is equal to 0. So I have k functions of all the variables which are equal to 0, where fi are linear functions, just like we studied in the assignment. So f1 is equal to a11 x1 plus a12 x2 plus a1n xn. Okay. Now I'm on the second equation, so I change the index, the first index to 2. A2 2 a 2n xn, and then you go all the way to fk, some number of linear equations. Okay, so this is similar looking stuff, but different setting. Similar to what we did with the vectors being expressed in terms of a basis. And actually, what I'm doing here is a special case of the above, because so note, this is a special case of what we discussed before, of the previous skill. Okay, since the linear functions from Fn to F form a vector space, and they have a nice basis. Let me call it E1. So what is the first function, linear function in my basis? Well, it's just the really simple function where it just takes the value of the x1 and forgets all the other ones. And then E2 is just x2. And then En is xn. So we have some really simple linear functions on Fn. There's n of them. Okay, and they're defined this way. And if you look at this equation, what we're saying is that this linear function can be expressed as a linear combination of the simple ones, right? A11 multiplied by this linear function, x1. So, the system, the linear system, consists of F1, Fn, where F1 is A11 E1 plus A1n En, and so on. Fk, a K1 E1 plus a Kn En. Okay, so this means that the problem is quite similar. So how are we going to approach this? So we're going to apply Gaussian elimination to this. So we will apply Gaussian elimination to the list F1 up to Fk to produce a new linear system. Linear system just means a list of linear equations. So this is a list, and each one of them is a linear function. So a linear system would just be, putting each of these linear functions just one after the other. Okay, so we're going to produce a new linear system, let's say G1 up to Gk. Okay, and the question is, what does this new system have to do with the old one, right? I mean, I'm going to change the equations. And then we're going to solve G1 equals G2 equals 0. Right? I'm going to look for the set of x such that G1 of x equals G2 of x equals Gk of x equals 0. Right? I'm going to solve the new system of equations. Okay, but the key point is that just think about the elementary row operations, right? If we take F1, right, and if I switch it with F2, right? If I had a point which was in the 0 set of F1 and of F2, And if I switch f1 and f2, then that same point will still be in the 0 set of both of them. Okay. Or if I take fi and send it to fi plus lambda fj, right? If I had a point in Rn which was a 0 of all of the fi's, right, then it would be a 0 of this and of this, and so it would be a 0 of the new linear function, right? And similarly, if I multiply fi by lambda, let's say, then a point which was in the solution set of the old vector of the old linear function will be in the new one. So you see that what's happening is that the solution set doesn't change, right? So a point which was in the solution set originally will be in the solution set of the new list of functions. A point x which was in the common 0 set of the fi will automatically be in the 0 set of the new g1 up to gk. Okay, and to complete the argument, I want to show that every point in the 0 set of all the g's must be in the 0 set of all the f's. So in other words, I want to show that the 0 sets of the f's and of the g's are exactly the same. And the reason for that is that all the elementary row operations are reversible. So if I have something in the 0 set of the g's, then I can do elementary row operations to get back to the f's. And therefore, it will be in the 0 set of the f's. So the same argument holds in reverse. Okay, so showing that that the 0 set of f1, so the zeros of f1 up to fk, is actually the same set as the zeros of g1 up to gk after applying any number of elementary row operations. Okay, so in this way, what you're doing is you're simplifying your system of equations until you get something which is much easier to solve. Actually, if you write your system of equations, and if it's in reduced row echelon form, then you can immediately solve the equations, and you can see how many solutions there are and so on. And so that's what I'm asking you to do in the latest assignment. Okay, I'll leave it there. Have a good weekend. And now we have office hours. So again, I'm just going to ask for if there's anyone who needs to go and who can't stay, please ask your question first. Like maybe I don't know, put your hand up and also put a thumbs up or something. Okay, I think I think we have a few people raising their hands.
Okay, so Bin, you have a question?
Yeah, for the last part, can you just give us a simple example for that? Like the old function changed to the new function and then...
Sure. Sure. So, yeah, so let's say that you start, let's say that you start with some equations that look like this. Say you have like x1 plus 2x2 plus x3 plus x4 equals 0, and let's say 2x1 plus 4x2 plus 5x3 plus 3x4 equals 0. And then we have, suppose 4x1 plus 8x2 plus 7x3 plus 4x4 equals 0. Okay, so what do I have here? I have 3 linear functions, f1, f2, and f3. These are linear functions of the variables x1 up to x4. Is that okay so far?
Yeah,
That I have 3 linear functions?
Yeah, of course.
Okay. And I'm looking for the common zero set. And what I explained before is that you can, so now what I'll do is just apply elementary row operations. So for example, I could multiply F1 by a constant. I could switch F1 and F2. I could scale, I could shear F2 and F3, right? And I'm going to get a new list of 3 functions. And I'm just going to massage this. I'm going to change the list of 3 functions until it looks simpler, right? So for example, if I take the first row, or let's say if I take, I'm going to use this 1 here. Actually, it's easier to just work on the matrix. So let me write the matrix really quickly. 1, 2, 1, 1, 2, 4, 5, 3, and 4, 8, 7, 4. Notice that I have to be sure that the same basis element x1, x1, x1 is here, and that's why I put 1, 2, and 4 here. It's because I'm expanding in a basis, and I've ordered the basis in each one of the rows. Okay, so now I have my matrix, and I can go to town and do my elementary row operations. So for example, what you could do is you could take the second row and send it to the second row minus 2 times the first row. Okay, so that's going to modify the second row. And I'm going to get 1, 2, 1, 1, and then 0, 0, 3, 1. Okay, and then there's a third row, 4, 8, 7, 4. Okay, but now I'm going to take the third row and send it to the third row minus 4 times the first row. Okay, and what am I going to get? I'm just going to get instead of 4874, I'm going to get 0030. Okay. Then next step. So what do I do now? Well, I need to find, so here I have my first echelon. Okay, and I don't have any echelons here, but here I need to look for which of the other rows has the earliest non-zero coefficient, and either one will do. Okay, so I'm going to, just for the fun of it, I'm going to switch the 2 and the 3 row. Okay, and what am I going to get? I'm going to get this. Then I'm going to scale 1/3 of row 2. I'm just doing normally I would do this faster, but I just want to make sure that everyone is following. Okay, and what will I get? Instead of 3, I'll get a 1. Okay, and then I can use my little psychopath here in row 2 to kill the 3 beneath it. So I'll get 1, 2, 1, 1, 0, 0, 1, 0, 0, 0, 0, 1. Okay, and I've got it in row echelon form. Okay, if I wanted, I could continue and I could do the backward pass and use this guy to kill everything above it and use this guy to kill everything above it. So if I wanted to, I could just subtract row 3 from row 1, and I could then subtract row 2 from row 1. And that would give me 1, 2, 0, 0, 0, 0, 1, 0. So this is, and then 0, 0, 0, 1. And then this would be in reduced row echelon form, and I'm done. Okay. And this operation was just taking R1 and sending it to R1 minus R3, and then R1 minus R2, and it doesn't really matter which order you do these in this particular case, though you should be careful. Normally, order does matter, and you should be very careful about doing more than one operation at once. If you wanted to be very careful, you would just do a single operation one at a time. Don't start doing multiple operations at once, because you may make an error, because the order matters. Okay, and then let's try to solve. So the new system, let me write the new system here. So it looks like G1, G2, G3. What is G1? It's x1 plus 2x2 plus x3 plus x4. G2 is, there's no x1, there's no x2, but there's an x3. And G3 has nothing except x4. Okay, and we need to solve G1 equals G2 equals G3 equals 0. Well, okay, you tell me which one is easier. The answer is x4 is equal to 0, x3 is equal to 0, right? And then x1 plus 2x2 is equal to 0. Okay, so what do we see here? So this is telling me that I can solve for x4, I can solve for x3, and I can solve for x1, but I cannot solve for x2 because there is no x2 echelon, which means that we cannot solve for x2. So what does that mean? It means that x2 could be anything. There's no unique solution for x2, right? So what we'll do is let x2 be a parameter. Let's say t, a parameter. Could be anything. Okay, and then we can solve for x1. x1 is equal to minus 2t. x2 is equal to t. x3 is equal to 0, and x4 is equal to 0. So the solution set is the set of minus 2t, t, or maybe writing it in a nicer way, it would be t times minus 2, 1, 0, 0, where t is in the field. Okay, and this is the solution set to the original problem. Hopefully, if we did it correctly, let me just grab this solution set. Can I go up? Let's go up here. Okay, and if you plug this in, minus 2, 1. So if I put minus 2, 1, it will be 0 here. If I put minus 2, 1, that's satisfied, and minus 2, 1 satisfied. So that is the solution set for this system.
Yeah, I got it. Thank you very much.
You're welcome.
Okay, Omar, you have a question?
Yeah. Just some clarifications. So the 0 set is the set of all functions which are equal to 0? If I'm not mistaken?
No. Try again.
Wait.
Just think more practically. What does the 0 set mean? You did it for you. Find the zeros of this polynomial. Find the zeros of this function. You did it.
It's the set of all the x values, or
yes,
the set of values which satisfy f1, f2, f3 equals to 0.
Yeah, it's the set of points in the vector space which are the 0, on which all the functions are 0. The first function being 0 is a constraint. The second function being 0 is another constraint. Third constraint, right? So you're finding the points which satisfy all the constraints. The points which are in the common 0 set of a certain number of linear functions.
So what's it called? So when we have the functions are not equal to 0,